Okay, good morning, everyone. I'm Sylvie Cortel, and I want to thank the co-organizer of this workshop, especially Vasu and Angela, and Sarah and Svante, who are going to organize the coffee and the questions today. So welcome to the Algebraic Combinatorics online workshop. Please note that the workshop is recorded and will be posted on YouTube. The speaker slides are available, I guess, on our website, but also will be available on the website of the conference. And once again, after the second talk, Sarah will be organizing a coffee time where we can socialize in random groups. So stay around. But for now, we're going to have two talks. And the first talk is by Lauren Williams from Harvard. And the title was already long, but there's even more now. There's a M equal to. So it's going to be a positive tropical Grassmannian, the hypersimplex, and the M equals to amplitude hydron. So thank you for giving this talk, Lauren.
So thank you very much to you and all of the organizers for organizing this workshop. I'm going to be speaking about joint work with Tomasz Lukowski and Matteo Parisi, and also separately on joint work with David Speyer. And my slides are available online. I have the URL on this title slide. So let me start by giving an overview of the talk. I want to discuss three different geometric objects. And the first one is a very new one called the Amplitude Hydron, which was introduced in 2013 by physicists Arkani-Hamed and Trnka in the context of scattering amplitudes in n=4 super Yang mills. And the second object is a more classical object. This is the hypersimplex and the moment map from the Grassmannian. And this was developed around 1987 by Gelfand, Goreski, McPherson, and Serganova. And then the third object is the positive tropical Grassmannian, which David Speyer and I introduced in a paper in 2005. And this object has some connections to the associate hedron and to cluster algebras. And I want to describe some relations between these three objects. So here's the outline. I'll start by giving some background on the Grassmannian and the amplitude hedron. I'll then introduce positroid triangulations of the amplitude hedron. And then I'll tell you about the positive tropical Grassmannian. And then I'll talk about positroid triangulations of the hypersimplex. And then I'm going to connect these two objects via this map that we call the T-duality map. And then I'll end with a conjecture, results, and a summary. So here's some background on the Grassmannian. So the Grassmannian GRKN over the real numbers is the set of vector spaces of dimension k in Rn. And as usual, I'll represent an element of the Grassmannian by a full rank k by n matrix. And then the k rows together span a subspace. So there's an example of a full rank 2 by 4 matrix. So of course, two full rank matrices can span the same subspace. So we should really think of the Grassmannian as full rank k by n matrices modulo a GLK equivalence. And it's very convenient to talk about Plücker coordinates on the Grassmannian. So given capital I, a k element subset of 1 through n, the Plücker coordinate P sub I is the minor, so it's the determinant of the k by k submatrix of A located in columns I. And then one can define the TNN, or totally non-negative Grassmannian, to be the subset of the real Grassmannian where all Plücker coordinates are non-negative. Of course, the Grassmannian one really thinks of as a projective object. And so to be more precise, I should define the totally non-negative Grassmannian to be the subset of the Grassmannian where all Plücker coordinates simultaneously have the same sign. And just as a historical remark, the definition that I'm giving is due to Postnikov from the early 2000s. Earlier, Lustig had defined the non-negative part of his generalized partial flag variety G mod P, but it's not obvious that in the case of the Grassmannian, Lustig's definition coincides with Postnikov's, but this is true and was first proved by Connie Reach in 2007. Okay, so I just put up at the top a reminder of the definition of the non-negative part of the Grassmannian. And now, inspired by the matroid stratification of the real Grassmannian, one can partition the TNN part into pieces based on which Plücker coordinates are strictly positive and which are 0. So more specifically, if M is a collection of k element subsets of 1 through n, so I'm thinking of this script M as a collection of Plücker coordinates, then you can define SMTNN to be the subset of the non-negative Grassmannian where your Plücker coordinate pi is strictly positive if and only if I belongs in your collection. So we're just going to partition the TNN Grassmannian into pieces based on which Plücker coordinates are strictly positive and which are 0. And then one of Postnikov's results from the early 2000s is that if this subset, SMTNN, is non-empty, then it is a cell, so i.e. homeomorphic to an open ball. So we call this a positroid cell. And then he showed that these cells are in bijection with various beautiful combinatorial objects. And so one of them is decorated permutations pi on 1 through n with k anti-exceedances. And I won't define it right now, but I will define it a bit later. And he showed the cells are also in bijection with various other nice combinatorial objects, including some equivalence classes of planar bicolored graphs. And I probably won't define these today, but there's a picture. Okay, now let me tell you about the amplituhedron. So the amplituhedron, A sub nkm, is now indexed by 3 positive numbers, nk and m. Like I said before, it was introduced by Arkani-Hamed and Trnka in 2013. And it's defined quite simply, actually. It's the image of the totally non-negative Grassmannian under a simple map. So let me tell you what is that map. So let's fix 3 positive numbers, n, k, and m, where k plus m is at most n. And now let's let Z be an n by k plus m matrix with maximal minors positive. So the k plus m by k plus m submatrices need to have positive determinants. And now I'll define a map Z tilde from the TNN Grassmannian to a different Grassmannian, the Grassmannian of k planes in k plus m space, and it just sends our k by n matrix A to A times Z. So A is a k by n matrix, and Z is a n by k plus m matrix. So when we multiply them, we get a k by k plus m matrix. The result, which is not obvious, is that this matrix is full rank and hence represents an element in the Grassmannian of k planes in k plus m space. So Z tilde is just a map from the TNN Grassmannian to another Grassmannian induced by matrix multiplication. And then the amplituhedron, A sub nkm of Z, is the image of the TNN Grassmannian under this map. So it's a subset of the Grassmannian of k planes in k plus m space. So let me make a few remarks about this object. So the first remark is that, of course, the definition of it depends on Z, but it seems that its combinatorial properties do not. It has full dimension k times m inside the Grassmannian where it's living. And the physicists introduced it because when m equals 4, its volume is supposed to compute scattering amplitudes in n equals 4 super Yang-Mills theory. And I'm really not going to say any more about this. So it got quite a lot of popular press when it was introduced. Wired magazine called it a jewel at the heart of quantum physics. And an artist came up with this picture. I'm not quite sure how. And it was also ranked number 10 among the 100 top stories of 2013 by Discover magazine. And another, I don't know where the artist came up with this picture either, but I will show some pictures in a few slides. Okay, so I know the definition probably went by quickly, so at the top I just have a review of the definition of the amplituhedron. And I'll just make a remark about some special cases. Oh, okay. First remark, despite the name, it's not a polytope. It's the image of the non-negative Grassmannian under a certain map. And the non-negative Grassmannian itself is not a polytope. So the amplituhedron certainly is not. But now for some special cases. If m equals n minus k, the amplituhedron recovers the TNN Grassmannian. If k equals 1, then the amplituhedron lies in the Grassmannian of, now, k planes in k plus m space. So this is 1 planes in 1 plus m space, which is the same as projective space. And it's not hard to see in this case that it's equivalent to a cyclic polytope with n vertices. And this was observed in the original paper. Like I said, m equals 4 is the case of main interest in physics. Now, m equals 2 is also very interesting, and that's what I'll mainly talk about today. When m is 1, the amplituhedron is again contained in a projective space, and it's homeomorphic to the bounded complex of the cyclic hyperplanar arrangement. So that's something that we proved a few years ago with Stephen Karp. And these are some pictures in the m equals 1 case from our paper with Stephen. They actually look not dissimilar from the artist renditions from Discovered magazine and Wired magazine. Okay, so here again is a review of the definition of the amplituhedron at the top. And now I want to talk about what physicists call triangulations of the amplituhedron. So first of all, the dimension of the amplituhedron is k times m, but this is in general smaller than the dimension of the Grassmannian that the amplituhedron is the image of. So in general, z tilde, which is the map defining the amplituhedron, is not injective. It's a highly surjective map. And let's recall that we have a cell decomposition of the TNN Grassmannian into positroid cells. And so a natural question to ask is to find a collection of km dimensional cells of the TNN Grassmannian where the amplituhedron map z tilde is injective, such that their images are disjoint and they cover a dense subset of the amplituhedron. Okay, so this is what the physicists call a triangulation of the amplituhedron. And despite the fact that we're going to use the word triangulation, images of cells are not in general simplicial. But I think they use this terminology because in the case that the amplituhedron recovers the cyclic polytope, you recover well-known triangulations of the cyclic polytope. Okay, so here again is a recap of the definition of triangulation. So we have this map z tilde defining the amplituhedron. So it's a map from the TNN Grassmannian GRKN to the amplituhedron contained in GRK k plus n. And the dimension of the image is k times m, which is smaller than the dimension of the domain. And so we define a triangulation to be a collection of km dimensional cells where z tilde is injective, such that their images are disjoint and cover a dense subset of the amplituhedron. And now let me mention this wild conjecture that we wrote down in a paper with Stephen Karp and Yan Zheng. So let's let m of a, b, c be this pretty product formula that will be familiar to many of you.
Lauren, may I interrupt you? There's some questions from people. So the one question is, if not a polytope, does that mean that it's not convex? Is that what does it mean that it's not a polytope amplitude?
Yeah, not convex, and it cannot even be, it's not even combinatorially equivalent to a polytope.
Okay, not even, okay. And the second question is, this triangulation, what are the boundary conditions?
So we're not yet making any boundary conditions. So so they might fit together in a very bad way, a priori.
A priori. Okay, thank you.
Yeah. Okay, so this wild conjecture. So let's first define m of a, b, c to be the number of plane partitions contained in an a by b by c box, which is this product formula. And so what we conjectured is that the number of cells in a triangulation of the amplituhedron A n k m for even m is m of k comma n minus k minus m comma m over 2. So we're saying that the number of cells in a triangulation is equal to the number of plane partitions contained in an appropriate box. And I say the conjecture is wild because it's based on really not very much evidence, but it is consistent with all of the known results or conjectures made for the case m equals 2, m equals 4, and k equals 1. And since it will be relevant for this talk, I want to mention that for m equals 2, this conjecture says there are n minus 2 choose k cells in a triangulation of the m equals 2 amplituhedron, so a sub n k 2. So this is the main object that we'll be talking about today. Okay, so a moment ago, one of you had a question about boundary conditions on triangulations, and I'm going to get to that now. So let's recall that a triangulation is simply a collection of cells, km dimensional cells, of the non-negative Grassmannian, where z tilde is injective, such that their images are disjoint and they cover the amplituhedron. Now, there are various known triangulations of the amplituhedron for certain values of n, k, and m, and many of the known triangulations are bad in the sense that boundaries of images of cells overlap badly. So it makes sense to impose some conditions on how boundaries should behave. And so a definition from our paper with Lukowski and Parisi is we say a triangulation is good if whenever the images of two cells, so z pi I and z pi j, whenever they intersect in codimension 1, we require that that intersection equals z pi, the image of a cell s pi, in the closure of the two cells you started with. Oh, I see a question in the chat. The wild conjecture is about all triangulations. Okay, so we want to ask that so when I define triangulations, I'm really only talking about the top dimensional pieces, the facets, and we're requiring that if we have two facets of a triangulation which intersect in codimension 1, then that common face of intersection should be the image of the cell which is in the closure of the two cells we started with. And one can do look at some data, and if you look at the number of good triangulations of the amplituhedron a sub n1 and 2, n1, 2, you get the Catalan number, which is given by this formula. And if you look at the number of good triangulations for the amplituhedron a n2, 2, then you get these numbers 1, 5, 48, 6, 93, for n is 4, 5, 6, and 7. And so when we saw these numbers, they were very striking because they're numbers that David Speyer and I had seen in an old paper in 2005. So the positive tropical Grassmannian, which I'll define properly in a few slides. So trop plus GRKN is a polyhedral fan, and the number of maximal cones in the positive tropical GR2N is the Catalan number. And the number of maximal cones for GR3N is 1, 5, 48, 6, 93, for N is 4, 5, 6, and 7. So you recover exactly these same numbers. So the question is, why should the amplituhedron, why should the M equals 2 amplituhedron be connected to the positive tropical Grassmannian? So this very strange coincidence was the starting point of our joint work. And you can refine the numerical coincidence that I have above. You can generalize the notion of good triangulation to good dissection, where you just drop the requirement that z tilde is injective. And you can look at the poset of good dissections, say of A722, and you get this F vector. And this is precisely the F vector of a related tropical positive Grassmannian. Okay, so it's a very striking numerical coincidence. So, okay, so I ought to tell you what is the positive tropical Grassmannian. And so first of all, one can define the positive tropical variety of the positive part of any tropical variety. And so that's what we did in our old paper. So given an ideal I in a polynomial ring, there's two equivalent ways of defining a positive tropical variety. And I'm just going to define them very vaguely because we don't really need the precise definition. But one way to define it is by computing the vanishing set over a positive Puiseux series and applying a certain valuation map and taking the closure. And another way is to take the intersection of positive tropical hypersurfaces associated to polynomials f in our ideal I. Okay, so if you haven't seen this before, you're not really meant to digest this statement, but it's but I'll make a more precise statement soon. Okay, but the upshot is that we can define the tropical positive Grassmannian as the intersection of a bunch of positive tropical hypersurfaces associated to all elements in the Plucher ideal I. And now it turns out that that in fact the three-term Plucher relations suffice. And so I can give you an even simpler, well, okay, this definition wasn't very simple. I can give you a simple definition of the positive tropical Grassmannian on the next slide. Okay, so how do we do that? So let's fix K and N, and I will let, I'll let P, this is going to be a vector in R to the N choose K, and its coordinates are indexed by K element subsets of 1 through N. And now we say that P is a positive tropical Plucher vector if for any numbers A, B, C, and D ordered, and any S, a K minus 2 element subset of 1 through N, disjoint from A, B, C, and D, either this inequality holds or this inequality holds. And if you've seen the three-term Plucher relation before, this should look reminiscent of it. And this is the positive tropical hypersurface associated to the three-term Plucher relation. Okay, so what's the upshot? Capital P, which lives here, is a positive tropical Plucher vector if a bunch of inequalities hold. And these inequalities all come from three-term Plucher relations. And the theorem that we proved with David Speyer and was independently proved by Arkani-Hamed, Lemons-Bredlin is that the positive tropical Grassmannian equals the set of positive tropical Plucher vectors. Okay, so anyway, so we have a reasonably simple definition of positive tropical Grassmannian. So it's a subset of R to the N choose K, and it has a natural fan structure as well, coming from looking at whether these inequalities are strict or not. Okay, so let me just give a recap of our two main geometric objects here, the Amplitude Hydron and the tropical positive Grassmannian. So if Z is an n by k plus 2 matrix with maximal minors positive, Z tilde gives us a map from the TNN Grassmannian to a related Grassmannian, just induced by matrix multiplication. And the Amplitude Hydron is the image of the TNN Grassmannian under this map. Meanwhile, the positive tropical Grassmannian is the set of positive tropical Plucher vectors. So this is just a bunch of points which satisfy a lot of inequalities. And what we observed numerically is that good triangulations of the Amplitude Hydron seem to be in bijection with maximal cones of the tropical positive Grassmannian. The question is why? So how can we relate the positive tropical Grassmannian to some kind of triangulations or subdivisions? And now our inspiration came from an old result of Kapranov, which was independently proved by Speyer. And this result related tropical Plucher vectors to regular matroidal subdivisions of the hypersimplex. And the hypersimplex is the moment map image of the Grassmannian. So what we're going to do is we'll find a positive analog of this statement. Okay, so let me tell you about the moment map and triangulations of the hypersimplex. So E1 through En will be the standard basis of Rn, and E sub capital I for capital I a subset will be just a sum of the corresponding E sub lowercase i's. And now the moment map is a map from the Grassmannian GRKN into Rn, defined as follows. So maybe I won't read it. At the bottom is just a normalizing factor. The numerator is a sum of the E sub i's weighted by norms of Plücker coordinates, and the whole thing is living in Rn. Now we define delta Kn to be the convex hull of E sub I, where I ranges over all K element subsets of 1 through N. This is called the hypersimplex, and this has dimension n-1. And the moment map image of the Grassmannian equals the moment map image of the non-negative Grassmannian and is the hypersimplex. And one can look at images of positroid cells and you get matroid polytopes, which are called positroid polytopes. So now, inspired by the definition of triangulation given by the physicists, we will define a positroid triangulation of delta Kn to be a collection S sub pi of n-1 dimensional cells of the TNN Grassmannian, where the moment map mu is injective and such that the images of these cells are disjoint and cover delta Kn. And as before, images of cells are not necessarily simplicial, so it's a sort of an abusive notation language to call this triangulation. So now one can try to construct regular subdivisions of the hypersimplex, and to do that we need a height function. So delta Kn has vertices, recall, indexed by all K element subsets of 1 through N. So the vertices are E sub I. So let's choose a height for every vertex. And so my collection of heights will be packaged into this vector P lying in R to the N choose K. So I'll think of this as a height function on the vertices E sub I. I lift E sub I to height P sub I. P sub I is just a real number. And now if we project the lower faces of this new lifted object to delta Kn, this gives a regular subdivision called D sub P. P, capital P, is our height function. And what we showed, which is a analog of the old result of Krenov and Speyer, is that if P is a vector in R to the N choose K, then the following statements are equivalent. So the first statement is that P is actually a positive tropical Plücker vector, so it obeys all of those tropical analogs of three-term Plücker relations. And the second statement is that every face of this regular subdivision is actually a positroid polytope. So this theorem is really just an analog of what was shown by Krenov and Speyer. If we delete the word positive here, and if we write matroid instead of positroid, that recovers this older result. We thought we would find the result in the literature. We didn't, although not surprisingly, it was anticipated by many other people. Speyer, early, Rincon, Willard, and appeared shortly after our paper in related work of Arkani-Hamed, Lamb, and Spredlin. Okay, but now back to triangulations. A corollary of this theorem is that regular positroid triangulations of the hypersimplex are in bijection with maximal cones of the positive tropical Grassmannian. So let me recap our two notions of triangulation. So first we have the amplituhedron map, Z tilde, from the TNN Grassmannian to the amplituhedron, defined via matrix multiplication. And then we have the moment map from a slightly different TNN Grassmannian to the hypersimplex, defined as follows. And we have two notions of triangulation. So a a triangulation for the amplituhedron is a, I have a typo here, I just realized. So a triangulation of the amplituhedron is a collection of 2K dimensional cells of the TNN Grassmannian where Z tilde is injective such that images are disjoint and cover the amplituhedron. And a triangulation of the hypersimplex is a collection of n minus 1 dimensional positroid cells of this related Grassmannian where the moment map is injective. And they cover the hypersimplex. So some small data, the small data that I showed you before suggests that maximal cones of the positive tropical Grassmannian are in bijection with good triangulations of the amplituhedron. And then the theorem I just mentioned says that maximal cones of the positive tropical Grassmannian are in bijection with the regular positroid triangulations of the hypersimplex. And so it seems that there is a connection here. So we'd like to understand what that is. Okay, so let's see. So let me give you a little bit more numerology. Well, okay, first of all, how could triangulations of these two objects possibly be related? It's very weird, right? Triangulations of the amplituhedron consist of 2K dimensional cells of GRKN. Triangulations of the hypersimplex consist of n-1 dimensional cells of a different Grassmannian. So it's very weird to see that there may be some connection. So nevertheless, let's compare the number of cells comprising triangulations on both sides. So according to our conjecture with Karp and Zhang, there should be n-2 choose k cells in any triangulation of the amplituhedron A and K2. Now Speyer made a conjecture in 2005 that there are at most n-2 choose k facets in any matroidal subdivision of the hypersimplex. So we see the same binomial coefficient coming up here. And David and I looked at the positroidal subdivisions of the hypersimplex, and we showed that every positroidal simplex has exactly n-2 choose k facets. Okay, so now I want to start to connect these two strange notions of triangulation. And for that, I need to tell you just a little bit about cells of the TNN Grassmannian. So Postnikov showed, so he defined decorated permutation to be a permutation where fixed points are either designated as loop or co-loop. And he showed that the cells S pi of the TNN Grassmannian are in bijection with decorated permutations on 1 through n with k anti-exceedances, where an anti-exceedance is a position I where pi of I is less than I, or pi of I is a fixed point, which is a co-loop. And you can read off the description of the cell from pi. Okay. And we have that triangulations of the amplituhedron consist of 2K dimensional cells of GRKN, and triangulations of the hypersimplex consist of n-1 dimensional cells of a related Grassmannian. So we have to map n-1 dimensional cells of GRK plus 1n to 2K dimensional cells of GRKN. Okay, so here's how we're going to do it. So let's start with a loopless decorated permutation pi written in list notation as a1 through an, and let's define pi hat by just cyclically rotating the entries of our permutation and declare any fixed point that pops up to be a loop. So what we showed, which is, this part is simple, is that the T-duality map gives a bijection between loopless cells of GRK plus 1n and co-loopless cells of GRK n. And moreover, you can say how the dimension gets affected. And in particular, this map takes cells of dimension n-1 to cells of dimension k. So this is our definition again. And now our conjecture, based on everything we've seen so far, is that a collection, S pi, of cells of grk plus 1 comma n gives a triangulation of the hypersimplex if and only if the related collection of cells obtained by applying T-duality to the permutation, so just cyclically rotating the permutation, gives a triangulation of the amplitude hydron ANK2. So it's a very, very simple statement, a very strange statement, I think. And we have some results in this direction. So first of all, triangulations of the amplitude hydron, which come from the positive tropical Grassmannian, in other words, the T-duality images of the regular positive triangulations of the hypersimplex behave well at their boundaries, so they're good. So that explains this numerical coincidence we saw for small values of k and n. Furthermore, there's a recursion that gives many triangulations of the hypersimplex. And I've drawn it pictorially here. There's a way to take a triangulation of a smaller hypersimplex and a triangulation of a different smaller hypersimplex and kind of glue them together to get a triangulation of delta k plus 1 comma n. So, okay, the upshot, there's a recursion that gives many triangulations of the hypersimplex, and separately, there's a recursion giving many triangulations of the amplitude hydron. The statement is due to Bao and He, and moreover, these triangulations are in bijection via this T-duality map. So this is a pictorial representation which shouldn't really make any sense unless you've seen playback graphs. And then another thing that we do is we introduce a momentum amplitude hydron, M sub nkm, which is supposed to play the role of the hypersimplex, but now should work for any even m, not just m equals 2. And this object generalizes an object defined in the case m equals 4 by Damgaard, Farrow, Lukowski, and Parisi. Okay, so I'll just end with a little summary. So on the one hand, we have this very classical object, which is the moment map, going from the Grassmannian of k plus 1 planes in n space to the hypersimplex. And everything in sight here is dimension n minus 1. And then on the other hand, we have this amplitude hydron map going from a related map, a related Grassmannian grkn to the amplitude hydron. And everything here is of dimension 2k. And then you can define the triangulation of the hypersimplex by using n minus 1 dimensional cells from this Grassmannian. On the other hand, you can define a triangulation of the amplitude hydron by using 2k dimensional cells of this Grassmannian. And the statement, which is not entirely proved, but there's a lot of evidence, is that T-duality is what connects triangulations on both sides. And so let me just end with this question. Why is it that the moment map is related to the amplitude hydron map? And how can we use this relation to better understand the amplitude hydron? And so, so thank you very much. And here's some pictures and the references again.
Okay, thank you very much. I guess we can all clap if we want. And I will let Svante handle the questions. I guess there were several during the talk.
Yes, so we had a few questions during the talk. A lot of them got answered by other participants in the chat. So I think we should try this differently now from what we did yesterday. So I think, please, everyone who has a question, raise your hand using the Zoom tool, and I can give you the question. So
should I stop my share?
Yes, you should.
Okay.
Oh, no, maybe you want to show. Okay, so maybe you want to show your slides again. Okay, so now I had Zachary Hamaker had the first question. please.
Yeah, so these triangulations of the amplituhedron are a little intimidating to me, but plane partitions are friendly. So I guess that's sort of twofold. One, does it look like any of the combinatorics of plane partitions, like the flip map, things like that, or like height functions? Do those extend to triangulations? And then on the other side, do the good triangulations have like a natural plane partition analog?
Right. So that's a great question. And one of the reasons the conjecture is so speculative is that we don't even, so what one would like to back up this conjecture is at least a conjectural triangulation for any amplituhedron where its pieces come from plane partitions. And we really can only do that when M is 2 and M is 4. And outside of those cases, we would like to, but we don't yet know how to map the combinatorics of plane partitions to triangulations of the amplituhedron.
Okay,
Yeah, so
thank you for that. The next question comes from Sam Hopkins.
Lauren, can you put your video back on?
Oh, is my video not on? You mean like you cannot see me?
I think the problem might be that now that we see everybody's video, that might be swamping the signal. So if you share your screen again, that might take care of the problem.
No, she's back now.
Oh, I'm back?
Yeah, you're back.
Good.
Well, we heard you all the time.
Okay.
Okay, now Sam.
So my question is about this duality between the triangulations of these sort of two objects of different dimension.
Mm-hmm.
Have you thought about if it could be seen as kind of an analog to the Cayley trick, which sort of similarly produces a bijection between subdivisions of different dimensional polytopes?
Oh, that's a great question. And I don't, I don't know right now if one could see it in that light.
Okay, are there any more questions or comments? Then you should raise your Zoom hand.
There's one in the chat. Oh, okay.
I think there was one question, what happens if M is odd?
Oh, right. So when M is odd, Stephen Karp and Yan Zhang and I have an analogous conjecture where now instead of having M over 2 as one of your components, you have like a floor of M over 2. But the conjecture has to be weakened in the sense that not all triangulations will use the same number of simplices. It's sort of like with cyclic polytopes, there's a difference between even and odd dimension. And so so anyway, so we have some version of the conjecture for M is odd, but not all triangulations will have the same size. So it really has to be a conjecture about the triangulations using the maximal number of simplices. But it again has the same spirit in terms of number of plane partitions fitting in a suitable box.
So Sarah, did you have a question?
Yeah, wonderful talk, Lauren. Thank you very much. So I was wondering if you've looked at the graph that goes along with this. It would be the analog of Young's lattice or Bruja order with this moment map.
So I don't know if this will answer your question, but we've looked a bit at adjacency of cells and triangulations, and in certain cases you get nice graphs recovering Young's lattice.
But that's, I guess, just for special cases, you mean? For special cases, yeah. But then what do the other ones look like? Do you still have nice properties like the rank 2 intervals or diamonds?
We don't know. We haven't looked at enough data to know, to have a good conjecture.
So somebody was asking if there's a formula for the numbers 1, 5, 48, 9, 63, or 6.
Oh, I don't know formula right now. No.
So thank you for this great talk. It's 8:45, so we're gonna switch to the next one.
Thank you.
Listen to Ron Adin.